and welcome to the fourth in my series of videos, all under the umbrella title of Absolute Relativity. And as we go on, later on I hope you will see it become obvious why I've called them absolute relativity, but they're all designed to give a new definition of what is happening at a quantum level. And quantum mechanics and quantum and nuclear physics, trying to overcome a lot of the unknowns, the mysteries, the weirdnesses that have led to what I've read described as fairy tale physics. And I kind of agree with that description. I do agree with that description. A lot of it makes sense. I hope you've seen my previous three videos. We started off with Young's double slit experiment, and then went on to quantum entanglement, and then we did the photoelectric effect, all of which were explained, simplified, vastly simplified, by the one realization that subatomic particles, particularly so far the photon and the electron, do not have independent existence. They are descriptions of the energy attributes of the nucleus of any atom. And I'm going to go on and show that all subatomic particles are like that, are just that, and nothing more. But now this video is going to be about photons and electrons, the nature of photons and electrons. And to start us off, you see on the screen there we have the classical Bohr diagram of a hydrogen atom, which is a single proton at the nucleus with an electron supposedly going circulating around it in orbit or in an orbital. An orbital being an indecisive cloud of electrons, which is so indecisive in its description that for me it just doesn't do it. But before we go on and talk about what in my description they actually are, this is, as I said, the diagram of the hydrogen atom. And if we go on and add, let me take that out and just bring this in. Here is the helium atom, and now you see you'll have two, of course we've got two protons and two neutrons in the nucleus, and according to quantum physics then every proton has its electron, making it neutral charge, and every time we add a proton with its accompanying neutron, then we get another element. So we've gone from hydrogen to helium to lithium, And now you see we have 3 protons, 3 neutrons, 3 electrons. There it is, standard sort of diagram. Now, before we go any further with that, I want to just discuss, because we will be looking at these shells. You see you've got this orbital here for these two, the first 2 electrons around these protons, and then you've got this further out one. We're going to be looking a bit more closely at that in this and the next video. The next video I produce is going to be on quantization, which is all about the energy levels of those different shells. That's what they're called. They're different shells. Let me just go back to, just to make it a little bit simpler, I'll go back to the helium atom, and now let's look at the protons and neutrons. The neutron has no charge, okay, but if somehow you can knock a neutron out of the nucleus and have a free neutron, it has a half-life of around 14 minutes, at which point it decays into a proton and an electron and a neutrino, electron neutrino, which is also negative. Now, neutrino is I'm going to be talking at some other time about this, but it's another little bit of energy. So what you have here is that bit is nothing more than the sorry, I've lost my, is nothing more than the hydrogen atom. It's a proton, electron. That's what it is. That's what it's there. It's just another proton with another little bit of energy, bit of negative energy. So what I'm going to do is come back to the hydrogen atom. So we've seen that the neutron is like an absorbed proton. When you go adding more protons together, you've got these neutrons that accompany them, and they're going to be absorbed into the system with this other little bit of energy, the neutrino. Sorry, that's an anti-neutrino, because it's negative. It's an anti-neutrino, but it's a little bit of energy. It's like an extra bit of energy. So it's a more energetic proton that is absorbed into the nucleus, helping to hold the whole thing together. And every time you add another proton, you get another element, and so on and so on. Add a proton and neutron, proton and neutron, you get another element, all the way through the periodic table of elements. So what we have in any nucleus is, in fact, a collection of protons. And the proton, let me just to there, the proton. Here, this is a hydrogen atom. The proton itself would be just the bare proton. Now, what we have here is a proton at a certain energy. Now, what we're doing is measuring this energy of this proton, which would be the binding energy of this proton would be 13.6 electron volts, and we're measuring that from somewhere outside. We're always measuring from something. We've got to find a system by which we can look at this, and it will only let us look at it from the outside. So there we are on the outside, and this system has an outer limit there. It has a boundary, and this is the boundary of the atom itself. And we are sitting out here reading this 13.6 electron volts here, and we're reading it this wise. So what we're reading is minus 13.6 electron volts. See, this is putting this out. We are reading in. So we are reading backwards along here. We are reading minus 13.6. There was no electron there to give us. So, you know, in the standard model, the electron is sitting there at 13.6, at minus 13.6 electron volts. So the whole thing is neutral charge, has no charge. But we're sitting out here. It's not being charged. It's not throwing us away. It's not throwing away or attracting in. So there's no charge when measured from out here. All we're measuring is this negative 13.6 electron volts. That's it. And the thing sits there. It's sitting there like this in its ground state. That's its lowest energy. It's actually not its lowest energy. It can go one lower than that, but we'll look at that a bit later. But it's sitting there in this ground state. Now, it neither really wants to take on energy or give out energy. It's quite, you know, it might be quite happy to sit there, but it will take on energy under certain circumstances. Energy comes in and energizes this photon. Now the photon, what I say, before I go on to that, the electrons have a spin. Everything spins. Well, I'm saying that this thing doesn't actually have independent existence. It's just a measure of the energy of this proton, which has spin. It sits there in its ground state, spinning away, and that's its ground state energy. More energy comes in, as I say, from elsewhere, from some energetic particle, from some energetic atom that's looking to dump its energy, and what happens is the proton then, which is already has its own angular momentum, spin angular momentum, then is given kinetic angular momentum out to the next level. Now don't forget that we're still out here measuring this. We're still on this boundary, and there's still 13.6 electron volts between there and there, and there. But now the proton is given this kinetic angular momentum. So what it's doing is spinning round like this. It's spinning, sent off, it's spinning round it goes, round. So it's got this angular momentum, and it's coming out to this limit now, which you will find this one is at 13.6 electron volts. This next one out is at a quarter of that, 13.6. It would be minus 13.6 electron volts divided by 4. Why divided by 4? Because we have these shells, and the shells go n equals 1, n equals 2, etc. Oops. I've pressed something and it's writing all the time. I didn't want it to do that. I don't know how to stop it doing that either. That's better. Sorry about that. None of this is scripted, as you will see. So, you know, we're going to have some scruffy drawings. We're going to have some cock-ups, but n equals 2. So it's gone from the first shell at n equals 1. And what we get is always 13.6 minus 13.6 electron volts divided by n squared. So in the first one, n equals 1, so it's 13.6. Second one, n equals 2. If we went out to the next one, n equals 3, so it would be 13.6 divided by 9. So this first shell is at minus 13.6. This next shell is at 13.6 divided by 4, which is 3.4 electron volts binding energy. So this thing has moved out. Its angular momentum is moving the energy levels out to here. Now what we've got is, now we are actually just 3.4 electron volts away from making this reaching this outer limit. That's what we need to see this as. 13.4 volts, electron volts only away from reaching this outer limit. And the more we go on, 13.6 divided by 9 gives us what, 1 point something or the other out here. So we're only 1 point something or the other electron volts away from the boundary, and everything else, the outside world, is sitting at that boundary. Now, just to, I'm going to shut that one down and open a new one. Give us a nice clean one again. So, we've gone from the proton sitting there at 13.6 electron volts as read from the outer boundary. Read from the outer boundary, that's read as minus 13.6 electron volts. Proton takes on some energy, so it's whizzing round its own. You know, remember, it's always still got its spin angular momentum. Now it's got kinetic angular momentum, taking it out to the next shell, which is minus 3.4. electron volts. Now, if this system is sitting there and it's now not at its ground level, it's getting more excited. This energy is exciting it so that it will be looking to dump that energy somewhere. And if there is another atom that's receptive to receive this extra energy, this energy between here and here, between minus 13.6 and minus 13.4, will give you 10.2 electron volts, will be instantly transferred. So this will drop down back to this level instantly, and that is a photon. And it's happening instantly because the drop down from one level to another within this atom is instantaneous as soon as it makes contact with whatever's picking up the extra energy there. And we would see that extra energy as light at a particular frequency, so a particular coloured light. So no electron needs to be involved to describe any of this. So that the photon is where the nucleus, where the excited nucleus has made contact with an outside atom and passed its extra energy on and immediately dropped down to its previous level. And if it gets excited out to the next one and drop down 2 levels, then of course the photon would be even more energetic and would be at a higher frequency and would be, you know, you got the red at one end and blue at the other, and that's what's happening. And so there's no electron involved. And just to make the point in all of this, let me see if it will let me take out all of these dirty marks. Quite often when I put enough dirty marks in there, it only lets me go so far, and that's all I can take out. Oh, that's it. But I can leave that there. I can work with that. So in the standard model, when the outside makes contact, makes this measurement, it's finding the electron. It's going to be somewhere in here. This cloud, you don't know. But I would say it depends on the state of the measurer, the receiver, the state of the outside and the condition of the inside. So, you know, it might make the measurement here, it might make the measurement here. It's not to mean there's a whole weird photon cloud going on there. No. All that's happening is, you know, it's going to measure here, measure here. It doesn't make any difference. You're inside this boundary. And when we give it kinetic energy and it moves out to the next shell, it's going to make, now this kinetic energy, it looks as though that you've got to imagine that these are spheres. So this thing is then moving round in this sphere, round and round in this sphere. So in effect, what that will look like is a donut. That's a cross section there. Look like a donut. And if we were to have a look at, leave that there. I'm going to show you in a second two diagrams of how that looks in what they call probability clouds. Don't go away. So just get rid of that and bring in these two. Let's start with this one. This is a description. This is a, remember when I was saying from outside you're likely to contact the, let's say this is outside, there's your nucleus, this is the ground state. So something outside is likely to contact here, here. So you have this probability cloud that's gathered around the center, because the proton is just sitting there with its spin angular momentum. And now if we energize that and give it kinetic angular momentum, remember it's spinning around here, so it's as though the spinning atom, which has its angular momentum, is spinning round its previous center, so that you're going to contact it here. So imagine this is a sphere, so this ends up a torus around here, a torus around there, and these are the probability all the way round of measuring the energy of that proton. That's it. These are not clouds of indeterminate, electrons in a superposition of states that could be somewhere and could be everywhere. No, the energy levels of the protons. And I say, when we look at, let me shut those two down. If I were to look at something here, come back to lithium, and this, I would say, is, instead of having a nucleus at the center here with these things revolving around them, I would have said that this whole thing is a description of the nucleus, and we have the neutrons binding this whole thing, helping bind this whole thing together, and these are the spinning protons. And these two in this shell, just all they have is opposite spins. We'll be looking more closely at that in the next video. But what I'm saying is that the this model is better described as take the electrons out and have put your protons in there. That's far better description. You don't need the electrons. The protons are at these energy levels. And so when one of these protons, if I say these are protons here, we've got energy levels, potential energy levels out here, but we've got a boundary out here that we're measuring from. Potential energy levels, if this proton shifts from this level, is given energy from outside, something outside dumps its energy into that, it moves out to this level. I've collapsed my I didn't want to collapse my that doesn't matter. Yeah, it does. I beg your pardon. Oh, what did I do with that? Layer editor. Yeah, sorry. I accidentally. You can see there'll be cock-ups, but there it is. I wanted this. I collapsed something that I needed, so I beg your pardon. You probably can't see that, but I seem to be fumbling, and actually I'm fumbling, but there it is. So when that proton takes on this energy, then is given more kinetic energy. We're still measuring on this boundary. We're not out the boundary on the energy level, but we're closer to it. But it will, if it finds another atom outside with which to dump this extra energy, that immediately falls down, which is why it happens immediately. Why also, because it's immediate, this transfer of energy from here to here is as immediate as this falling from one level to another. That's it. That's energy is then transferred. That's gone. That's instantaneous. So effectively, because it's instantaneous, this particle with which we're communicating, this other atom, could be anywhere. There's no distance. Photons don't see any distance. There it is. They're your photons. They're your energy levels of the protons in this system. Now I'm going to come out of that again and bring us back to the hydrogen atom. So now we've seen what constitutes a photon when this atom is jumping from one level to another, and it's jumping from one level to another because it's being given energy from somewhere outside, and it's giving out energy in the form of what we would perceive as light, electromagnetic waves. Now, as we move out these shells, as I say, we go from minus 13.6 eV to minus 3.4 eV. You see how we're getting closer to zero, and zero is our boundary where the rest of the world is sitting. Now, if this continues to take on more energy, it goes through its different shells, then it gets to this. So we've got to say that when it gets to this level, when this proton has enough kinetic energy that it is... Oh no, I didn't want to put that line in there. Anyway, I don't know what I've done now. Don't know how to stop it doing that. Oh, hang on a sec. Another cock up. When this proton has in it's running this double line thing now. I don't know how to stop it doing that. There. When this proton has enough energy that the 13.4 electron volts that the proton is ordinarily sitting at, that we're measuring across here, now we're out to that limit, so that the 13.4 electron volts is taken out to that limit, and it then moves out. The whole atom boundary moves out. There's nothing to stop it. It's overcome its boundary, so it's moving out into the outside world, whatever that is, whether it's into gas, into a vacuum, whatever it is. This atom is then moving out. It's succumb its boundary. It's taken off. It's taken up enough energy to move out into the outside medium, whatever that happens to be, and that is perceived as the hydrogen atom losing its electron, because it's lost, in this classical view, this electron is what's stopping it, is what's making it neutral. But now it's not neutral, it's moving out into the outside world. So what we see that as, there's no negative values there. This is positive now. It's lost this negativity and it's positively moving out. So that's positive charge. So this becomes ionized. This atom is now ionized and it's moving out with positive charge into the outside world. And that, because it is moving out, it is perceived as having mass, where the photon, because its effect was instantaneous. Now we're moving out at a very fast rate, something close to the speed of light, but it isn't. Now we've seen that this has supposedly, because it has space and time, it has movement, it recognizes space and time, it has supposedly it has mass, where the photon, because it moves through space and time instantaneously, has no mass. Of course the photon does have mass, and so does the electron. The photon transfers mass as the electron does, but the photon does it instantaneously by this quantum leap, and the electron moves out. That's it. That's the nature of the photon and the electron. So that the positively charged, get back to this, the positively charged, the ionized proton is just a proton. and it is in contact with the outside world because it is supposedly an ionized hydrogen atom. Now, when it drops down, back down to its ground state, then we have this boundary. It's not communicating. We have this boundary that measures at the minus 13.6 electron volts. However, this proton at the center can, under certain circumstances, give up some energy. And when it does, it will sit there at, where is it now? I've got a now. It's given up some energy, and it sits there at 13.6. It loses, it sits there at minus, here's my pen here, at minus 14.36. Let me scrub that out. You probably can't see it. I'll probably write that too. 14.36 eV, electron volts. It then has slowed down its angular momentum. Because remember, when it's sitting at its ground state, it just has angular momentum. It has no kinetic angular momentum. But now, under certain circumstances, it can drop down again to minus 14.6 eV, which means it's actually slowed down. Now, unlike when it reaches its boundary, it's seen to lose the electron. Now, because it's still supposedly, by the old standard, has its electron, but now it's gone down further. It's lost energy still further. It's down here. So the only way that the standard model, if you like, can show that as another electron. Okay, it supposedly has received another electron. Well, it hasn't. It hasn't received another electron. It's just gone. It's been forced to go more negative. Now, the effect of that is that it becomes negatively charged, because sitting there at its minus 13.6, this is the balance of it. So it's neither positive nor negative. When it's charged to that level, then it becomes positively charged, but now we've dropped it down below that level, so of course it's now negatively charged. It hasn't picked up another electron. The electrons doesn't exist. All that's happened is that the proton has lost energy. That's it. The whole thing then is described in terms of proton energy. And by the way, when we were talking about the fact that when it's positively charged, it is moving out, it's succumbed its boundaries, it's moving out into the outside world. So therefore you have this motion, you have this space and time effect, so that it supposedly has mass, but the photon, because it's just jumping between these two internally, So it's dumping this energy. It's in contact with the external receiving atom, dumping the energy, shifting down. The whole thing's immediate. So that we don't need this thing. We don't need the Higgs boson to explain why the electron has mass and the photon does not. There it is. The whole thing explained in terms of the energy levels, the energy attributes of the proton. No Higgs, no photon, no electron. Protons and neutrons, and a neutron is a slightly more energetic proton. There you have it. What I'm going to do next time in the 5th video is talk about these energy levels, these energy shells. So the next video I'm going to produce is going to be on quantization, and again I'm going to be looking at the whole thing in terms of energy levels of protons. That's it. So we'll have a cock up just to finish with. So let me bring it back to something cleaner, so we're not all messed up. There you go. I'm going to end there. Hopefully, hope that all made sense, and I hope you'll want to join me in the next video, as I said, on quantization. See you then. Goodbye.